Hi, I'm Michael Koval, and I'm going to present our recent work on pre- and post-contact policy decomposition for planar contact manipulation under uncertainty. This is work done jointly with my advisors, Nancy Pollard and Srinivasa at CMU. We're interested in getting robots to physically interact with the environment around them, just like the previous speaker said. So grasping, pulling, pushing, otherwise manipulating the environment. And these actions generally suffer from uncertainty. There's uncertainty in the pose of the object. We don't have perfect perception, and our proprioception of where the hand is, and our physics models we use while planning. We propose to deal with this uncertainty using real-time feedback from contact sensors. And we formulate this problem as a POM-DP. So in general, in particular, we consider a POM-DP where state is pose of the object relative to the hand. Actions are relative motions of the end effector, which may push the object if you come in contact with it. And observations are binary readings from contact sensors, which may cover part of the hand surface. Our goal is to optimize some task-dependent reward function, which may, for example, drive the object to be graspable or into some region in the hand frame. Of course, solving a POM-DP is in general p-space complete and not tractable on large problems, but we found some specific structure in this particular problem which we believe makes it tractable to run this type of policy in real time. In particular, we've noticed that the optimal policy naturally decomposes into pre- and post-contact stages. And let's step through a simple example to see what I mean. So suppose we execute this type of trajectory and we observe contact with our left fingertip. We might get a posterior distribution that looks something like that. If we execute a different trajectory and observe contact with our left fingertip, receive a very similar posterior distribution. And in fact, the same thing is true if we do the same thing on a completely different prior distribution. In general, what we've observed is that there's a relatively small set of post-contact belief states. This is true fundamentally because contact sensors measure contact on a lower dimensional manifold in the state space. This means that everything that's not on that lower dimensional manifold is very low probability. So we can use this structure to decompose the problem into two stages that are loosely coupled. We have a pre-contact stage which tries to make initial contact with the object. Then we have a post-contact stage that's some complicated closed-loop policy which achieves the final grasp. And our observation is that we can pre-compute this post-contact stage and run an efficient search to solve the pre-contact stage online. So first, I'm going to discuss this post-contact stage. At a high level, we just discretize the state space near the hand and solve it exhaustively using a point-based method. However, we have to be a little bit careful about how we do our discretization. You can't simply uniformly discretize the state space because this misses the ability for contact sensors to differentiate between contact and no contact. Instead, we discretize free space uniformly and also discretize the surface of the contact manifold, which is this two-dimensional subspace of objects that are in non-penetrating contact with the hand. If you discretize your problem this way and solve using your favorite point-based solver, you get policies that look something like this. These policies use information gathering actions to localize the object and successfully get it into the blue goal region centered in front of the palm. However, these policies are only valid for post-contact belief states because that's all we've pre-computed them for. So we must now solve for a pre-contact trajectory that generalizes these policies to an arbitrary prior. We do this using an A-star search in belief space. This is efficient because we've pre-computed the solution for all post-contact nodes. This means that instead of branching on both actions and observations, we're now only branching on actions. Our post-contact policy is simply a trajectory or a sequence of actions that we execute until we observe contact with the object. In the paper, we have a proof that shows this decomposition has a bounded effect on the suboptimality of the overall policy. Additionally, we found that if you run a large number of simulations, our policy, shown in orange, significantly outperforms a baseline QMDP policy, which does not consider information gathering during planning. So this is what the full policy looks like. You'll notice that it still has the rich information gathering actions of the post-contact policy, but we can now apply this to a new prior without duplicating all of that pre-computation. So thank you, and if you're interested in hearing more, please talk to me during the poster session, F2.
Hello everyone, my name is Mohammad and I'm presenting our paper which is about introducing a new paradigm to integrate motion generation and impedance control into a single unified control policy. Before presenting our approach, let's have a look at one of the most widely used control techniques. In this approach, there is a time index reference trajectory which is generated offline. And then we have a PD controller that tries to follow this reference trajectory as closely as possible. We have seen successful implementation of this control approach in many industrial applications. However, if we have the vision to bring robots into human environment, this approach is prone to failure because of two main aspects. First, it doesn't provide any adaptation to dynamic environment, which is crucial. And second, it imposes this limitation that to make the robot safe, we need to sacrifice accuracy. Each of these problems have been studied separately in the fields of feedback motion planning, and the second one in the field of variable impedance control. However, for successful execution of many tasks, we need to have both features at the same time. To reach this goal, one possible solution is to use a two-loop control architecture, as we could see here. The outer loop includes feedback motion planning, which in real time generates a path for the inner loop, which is a variable impedance controller. And this inner loop also determines the robot behavior when it comes into contact with the environment. However, there are several challenges that are associated to this control architecture. First, ensuring stability of variable impedance control by itself is a difficult problem, and only a few studies have been done in this direction. Second, addition of feedback motion planning even makes a stability analysis much more complex. At this point, we thought maybe we should revisit the problem and try to come up with a simpler solution to this problem. And we noticed that, in fact, it makes much more sense to merge the two control loops into one single control loop by using a more advanced control technique. And that is what this paper is about, to unify motion generation and impedance control. Let's take an example why it's important to merge the two loops together. So in this example, the robot should reach the red box, and in the middle of the task, the human user pushes the robot toward the right side. At this point, the impedance controller tries to resist against this perturbation, whereas the motion generation wants to adapt a new path without any resistance. So we could see that the two loops are conflicting each other. And that is why it's important to have one single control policy that can do both jobs at the same time. Our approach is called iMogic. Yeah, so it's called iMogic, and as it comes from its names, it can model both motion and interaction in one single model. To evaluate the stability of iMogic, we use the well-known rigid body dynamics of equation. Here I would like to emphasize that in our stability analysis, we do not need to know the exact value of the external force, which is really good because this value is not always available. Our control policy, in fact, is a nonlinear weighted sum of a set of spring damper systems. You could think of it as a set of spring dampers that are spread in the task space. And the region of influence of each spring damper is defined by the nonlinear weights omega. Here I would like to emphasize that the notion that if the stiffness and damping are positive definite is sufficient to ensure stability of the system is wrong. And in fact, in nonlinear systems, it's important also to look at the weight omega. And in our paper, we provide sufficient conditions on the nonlinear base to ensure global asymptotic stability of the system for free space movements. And it's a stability when it comes to contact with passive environment without any knowledge of the contact force. Here's an example of using iMogic to control the KUKA lightweight robot. The task is simple. The robot should just reach the surface of the table. But here I would like to emphasize that there is no reference trajectory. The robot motion and its interaction with the environment just naturally comes based on the situation the robot is. Let's have a closer look at the energy levels of the control policy. So here, in the highlighted region, we designed the control policy to be compliant, and we have almost zero stiffness in this region. And that is why the human user can easily move the robot along the z-axis. Along the x and y axis, we designed the control policy to be stiff, which means that it pushes back the robot toward the compliant region. And as we could see, the robot is completely compliant and passive, and is stable. there are many things to talk about, and if you're interested, please come to our poster at F3. Thank you.
All right, I'm Katie Bill, and I'm presenting work that I've done with my student, Aude Saglam. And our title's a bit of a mouthful, so I'm going to try to break down the key concepts. The first of which is that we're dealing with rough terrain walking. So we have a planar walker, which has a passive pivot point at the ground. But more generally, we're trying to deal with any robotic system in which there's enough under actuation, an uncertainty about the environment, that we can't strictly say that we're stable. In fact, we're going to say with probability 1 that the system's going to fall down. We know the Google car is going to crash, but we don't want it to do it very often. And the way we do that is by coming up with the right policies. So we want a policy that's geared toward taking the greatest number of steps possible and uses noisy information about the state and the environment. There are some other keywords here worth discussing before I move on. This middle one might be confusing. This term metastable simply means not strictly stable, but very rarely failing. And so for a walking system, we can imagine when it's noisy, you're walking around in a neighborhood of state space for a very long period of time, but eventually you transition to a more stable fallen down state with probability 1. Even though they say diamonds are forever, they're in fact metastable. The next idea is we want to mesh this system because we want to treat it like a Markov decision process. And so that meshing takes place both event-based, once per step we're going to mesh, and also we're going to take a continuous state space and represent it with discrete states. There's nothing particularly unique about these last two ideas. We've been thinking about it in our lab for a while. However, we're finally applying this to much higher dimensional systems. And you have to go to the poster session to find out how. It involves using low dimensional controllers. But to be specific, our walker here has 5 links, so that's position variables. Each of those links has a velocity, that's 10 states. And we're somehow able to deal with the curse of dimensionality by basically projecting things onto low dimensional manifolds. The last aspect for our work for this RSS paper is that we're trying to be robust. So we want a control policy that's insensitive to noise, both we're being pushed around and we've got bad information about what's happening up ahead. But we also want to be insensitive to modeling errors. And we know that modeling errors are important because we know we're meshing. We know that that's not an exact representation of the dynamics. Okay, so our motivation is imagine that you're walking blind. If you had even a limited look ahead of what's going to happen on terrain, intuitively this should be incredibly helpful because you can adjust your gait to walk down and to walk up again. Very intuitive. But what we want to do is to quantify how useful is that look ahead. And so the approach we're going to use is to design these low-level controllers. Here's an example of one controller. And intuitively, what it's doing, it's got a torso that's biasing it to walk forward just a little bit to recover energy, and it's lifting its feet nicely on terrain. It has a stable limit cycle when it's on flat ground. And if we move it over to rough terrain, it'll walk for a while. But especially when it's going uphill, eventually this thing is going to trip. So one thing we want to do is we want to say, well, how do we give this guy a score for the number of steps it takes? We don't want to just run Monte Carlo trials. When it's taking a lot of steps, we want a more clever way to do that. We have some machinery to do that. At the end of the day, we're trying to come up with something we call the mean first passage time, which is just the mean time between errors. And the way we want to improve that mean first passage time is to switch between a family of low-level controllers. And that's also the key that helps us do this meshing for this problem. So if you look in the bottom left before this guy fails, he's leaning forward because he's designed to go uphill. He tends to fail when he's going downhill. So we got 2 controllers, and we added a third just because when we did experiments, we found having 3 controllers was sort of a sweet spot. We didn't need really more than that to do very well. And so our goal is to come up with the right policies, once per step, based on 1 step look ahead on terrain, to decide which of these 3 guys to use. We do that, and we come up with optimal policies, but again, remember, that's for our mesh system. And when we run that on the real system, you can see it leaning forward when it's going to go uphill, getting more upright when it's trying to go downhill. Eventually, we saw for the real system dynamics, when we simulated this, it would fall more often than we wanted. So a real key in this was to try to get more robustness, try to mesh higher dimensional spaces, get robustness. You can try to predict which way he's going to go as he's walking there. And the key to doing that was going back to that MDP, the Markov decision process, and adding some uncertainty about what state we're in and what those transitions were going to be. And we found we actually were able to get remarkably good performance. So again, thanks for your attention. We, Olz and myself, are from the University of California at Santa Barbara, which is almost as nice as the campus here at Berkeley. We're about 5 hours south if you ever want to come and visit us. And finally, a silly plug for our poster at the end, so you'll remember it. It's after lunch, a long time from now. It's poster F4, which is extremely easy to remember because 4 begins with the letter F. And it's kind of a self-referential number because it has 1, 2, 3, 4 letters. Thanks very much.
Hi, I have a question for F4. In your model, what did you use as control inputs? Were those torque inputs at the joints or straight angular velocity inputs?
Those are torque inputs at the joints. So the low-level controller has reference trajectories that it's trying to match. We use a sliding mode control so that we get finite time convergence for those. It's a really interesting question how we design the low-level controllers. I tried to design it to tell you intuitively. We're trying to lean forward a certain amount, leaning forward more, going uphill. It's torque inputs at the end of the day.
Other question? No. Can we bring the microphone here?
I can talk loudly. So for F4, how applicable is the control strategy to some other system where it's completely different than walking, but you want to use different controllers based on the situation, and it can potentially become unstable?
Interesting question. We would say highly applicable. Please use these methods. That's why I kind of hinted at the Google car. We're trying to use it on other types of walking systems, higher dimensional humanoids, higher dimensional kind of bounding models. The key that we think is that you're not blindly trying to find control actions at an incredibly low level, that you're really smart enough as a controller that you have some middle level idea of, okay, like I have basic rules, but I know that I'm going to have noise, I'm going to have options between picking these rules, and I have to find the best way to do that. So the key is that you put in enough structure to have some options rather than going down to, say, the torque level for control switching. But yeah, we're waiting to see someone else kind of grab onto these ideas.
Are there other questions? Can I ask about F3? What are the type of more challenging problems that you're thinking of applying the method?
So I think there are many interesting applications to that, because many real-world robotic tasks requires both motion and interaction at the same time. Just think of like a robot cleaning a table to sewing and many other fine manipulation tasks. And currently people do that by separating the two problems, like using a hybrid control. But whereas our control approach, we could just use one single model to do that, so we don't need to decompose the problem into like two different things.
Well, let's thank the speakers. We're going to now transition to the second part.
Hi, I'm Jiefu. I'm here to present my work on learning-based control synthesis method for temporal logic constraints in unknown stochastic system. This is a joint work with Ufuk Topcu from University of Pennsylvania. So a big challenge in design a good controller is the uncertainty and unknown in the system dynamics. The objective here is we are particularly interested in temporal logic constraints. So given an unknown and stochastic system, how can we synthesize a policy that maximizes the probability of satisfying the temporal logic constraint with a polynomial time, space, and sample complexity? So existing synthesis algorithm for temporal logic constraints give us this optimal controller if you have perfect knowledge about the model of the system. On the other hand, reinforcement learning has been developed to construct adaptive control policy, but it's not applicable for to handle temporal logic constraints. So in this work, we are trying to bridge these two together to solve this problem. So we consider PARC-MDP method. PARC stands for probably, approximately, correct. Compared to statistical learning, PARC method ensures with high probability we can obtain a near optimal policy with a polynomial time, space, and sample complexity. But to extend the PARC-MDP method with a linear temporal logic constraint is not straightforward, because the reward structure for temporal logic is different from the traditional reward structure in PARC-MDP. Suppose in this example, you see a robot, which is a blue dot, trying to visit the region R1, R2, and R3. In this order, we are avoiding the red cells. So we reward the behavior not depending on which state the robot is in, but we look at the infinite state history and see if this infinite state sequence satisfies the temporal logic constraint. If it satisfies, we give a reward 1. If it does not, we give a reward 0. So there is a normal Koval property and a non-discounting or average reward structure if you want to consider temporal logic formula as a control objective. So we developed an algorithm to handle this particular reward structure in LTL specification, and then we develop an exploitation and exploration mechanism such that either the current policy is already near optimal, or the system will explore some unknown regions in the underlying MDP with non-zero probability. So the main result of this paper is that when given some confidence level delta and some approximation parameter epsilon and the temporal logic formula, our policy can converge with confidence 1 minus delta to the near optimal policy with respect to satisfying the temporal logic constraints. And the convergence is guaranteed with a finite number of samples at finite time, which is polynomial in the size of the MDP, the specification, which is a temporal logic formula, 1 over delta, 1 over epsilon, and t, which is the state value mixing time. So we apply this algorithm to this previous simple example with epsilon equal to 0.01 and confidence level 95%. So there, in that example, the robot have uncertain movement in all 4 different directions. And the region is partitioned into different terrains, including grass, sand, pavement, and gravel. The transition probability in all 4 different terrains are different for this robot movement. So the robot starts randomly explore, and once he learns some terrain, it is more balanced towards the unknown regions and trying to explore more and increase its knowledge about the underlying MDP. And once the robot explores other regions, with this epsilon equal to 0.01, we actually converge to the optimal policy for this task. So as you see, after all regions are known, the robot converges to the optimal policy and makes the best action at each grade. And with this uncertainty in its movement and trying to maximize the probability of satisfying to visit this R1, R2, and R3, we are avoiding all the red cells. So we can actually modify the parameters to make a trade-off between the convergence time and the suboptimality of your policy. So our main contribution is to develop a method, Park MDP method to handle temporal logic constraints. And if you are interested in this work and also future directions, please come to my poster session at F5. Thanks.
Hello, I'm Yano. I'm a PhD student in ETH theory, and I will talk about self-calibration and visual plan with the multi-camera system on the MEV. So now we want to demonstrate real-time onboard multi-camera plan with loop closure. And before we can do plan, we need to develop a self-calibration algorithm to estimate the camera IMU transform. It's very important that they are very accurate if you want to do plan properly. Now the motivation of using multi-camera system is that we get a 360-degree field of view, and therefore we will get more robust RAM and localization because we get more physical correspondence, we have more complete 3D map, and we have less constrained path planning. Now we use 2 assumptions. The first one is that we arrange each pair of camera in a 0 configuration so that we get 3D data. And we use the 3D data to ensure matricial, and also we assume that we know the relative rotation, and because we reduce the complexity of the motion estimation, I think we only need to estimate the translation. So now we show our MEV platform, which is the Firefly helicopter. We have a 4-camera system where all the 4 cameras are synchronized, and we use a fixed eye length for each camera, and we make sure that all the sensor and computer board are time synchronized, and we meet the code open source. So now we will talk about the SLAM-based self-calibration, which works for a system with an IMU and any number of calibrated 0 cameras. Here we only use natural feature. We don't use special marker, and we only require minimal human intervention. So now the idea behind self-calibration is that we put a map for each 0 camera. We find feature correspondence between the different 0 cameras, and then we want zone optimization to optimize all the parameters. So now we show the visual autometry for ECU camera, and then after that we look for loop closure. We want program optimization and bundle adjustment to get the map for each CO camera. And then we have the two map, and we combine the two map into one. And then we look for loop closures between different CO cameras. They are very important because they are very strong prior for accurate inter-CO camera transform. Now, after we add the loop closures between the different CO cameras, you run program and zone optimization to get the map and the calibration parameter. And now you want to check how accurate the camera and IMU transform are. So we use the Falcon motion capture system and the chatbot to get the ground truth data. And we see that we get no rotation and translation error. And also we check how accurate the pulses from depth calibration are. And we can see that the pulses are quite accurate, and it means the depth calibration is quite accurate. Now you will talk about the visual plan. We do loop closure. It can run in constant time because of the double window optimization. And also we have a novel 3-point algorithm for a multi-camera system. We can estimate the relative voltage. We can estimate the relative motion with material. So here we have the generalized epipolar constraint. We substitute in the rotation from the IMU, and we get a minimal and linear 3-point solution. And the good thing about it is that we do not require simple triangulation. So now we show a visualization of an indoor environment where the MEV flies 3 loops. So now the MEV is flying the first loop is coming back to the same place, and we can see that their loop closure is shown by the green line. And on the left, we optimize the fitting keyframe in the auto window, and on the right, we optimize all the keyframes, but it's not constant time, and the error is slightly smaller. And we do one large loop in an outdoor environment, and we have a loop closure error of 2.93%. So now we have shown our land-based calibration, which is able to estimate accurate calibration parameter. We also have a 3-point algorithm to estimate relative voltage motion with material, and we have done real-world experiment. Okay, thank you.
Thank you. My name is Rick Zhang. I work with Marco Pavoni at Stanford University. Our work focuses on understanding and controlling a fleet of robotic shared vehicles and how they might benefit society. Now, I'm sure I don't have to convince many of you that autonomous cars are the future. Google is doing a fantastic job of that. But when we finally have these vehicles, arguably the most promising approach is to have a shared fleet of self-driving cars that provide point-to-point service with the same convenience as private automobiles. Now, this idea essentially combines car sharing with vehicle autonomy to provide what we call autonomous mobility on demand. Now, the first problem you run into is something called rebalancing problem. Because some destinations are more popular than others, some cars will inevitably so some parts of the city will aggregate more cars and other parts will be depleted of cars. So the cars have to drive themselves to rebalance the system. Our objectives are to develop a stochastic models and analyze the potential benefits and drawbacks of these systems. We developed a closed Jackson network model, which is based on the theory from operations research. We call it the passenger loss model because the key point is when passengers request vehicles and the vehicles are not immediately available, the customer leaves the system. This not only simplifies our analysis, but it appears to be suitable for systems where high quality of service is desired. Our performance criterion is then the probability that a customer will find an available vehicle. Now, we can show that without rebalancing, most of the stations in the city will never reach an availability of 100%, no matter how many vehicles you have. But if you have the optimal rebalancing policy, then the availability of each station is the same, and they approach 100% as you increase the number of vehicles, which is what you would expect. We showed that optimal rebalancing rates can be solved as a linear program, which allows us to handle very large systems of hundreds of stations and thousands of cars. We applied our approach to a case study of Manhattan using real taxi data to generate passenger demands in a hypothetical autonomous MOD system. Taking inspiration from our queuing model, we developed a real-time rebalancing policy that works very well in simulation. We simulated the customer's demands throughout the day and estimated the customer's waiting time. This particular simulation you see has 7,000 vehicles. The green bars are the vehicles waiting at the stations, and the red bars are the customers waiting. And the dark blue dots are the rebalancing vehicles. So if you look very closely, you can see the rebalancing vehicles traveling to the stations where the customers are waiting. Now, both our queuing model and our simulations suggest that 7,000 to 8,000 vehicles would be able to achieve a high quality of service in Manhattan. To put this in perspective, there are over 13,000 taxis in Manhattan, and about 85% of all trips are within Manhattan. So I would say our system is comparing favorably to those. Finally, I must confess that until now, I haven't really included any congestion analysis in the system. But the question of whether autonomous MOD systems will increase congestion is currently very hotly debated, because for the same number of passenger trips, you actually have more vehicles on the road because of this rebalancing. So we delve into this problem a little bit by simulating many randomly generated systems on this very simple 9-station road network. And what we find is that rebalancing does indeed increase the vehicle density on the road network for most of the road segments, but not the road segment that's already the most congested. That's that red one that's near the middle. Now, this suggests that rebalancing vehicles tend to travel along less congested roads and may not necessarily increase the congestion in the system. So in conclusion, we developed a stochastic, rigorous approach to the system-wide coordination of autonomous MOD systems, and our work opens up numerous doors to future extensions, such as controlling human-driven MOD systems, electric car charging, intermodal systems with public transit, and many more. Thank you for your attention, and please check out our poster session at F7.
I would like to point out that the last talk is a candidate for a Best Paper Award. We have our 3 speakers. Are there questions? Yes. Here, let's wait for the microphone.
So for the last paper there, if one was to implement something like this, obviously you can't just evaporate the infrastructure that's there and completely replace it with what you're proposing.
Right.
Have you looked at partial solutions and the consequences of that?
Yeah, so I think, I'm okay, thanks. I think when you actually implement the system, and it's a very good question, that likely what you would have is more stations around the suburbs of the city where there's more parking spaces available, and you might have, in the inside of the city, just vehicles loitering around like taxis do. Of course, this could potentially increase the congestion even more, and we're in the process of looking at that.
We had one question here. Here at the center. Raise your hand.
So this is for Rick again. How does it scale with the number of stations? Because ideally, you wouldn't want to have to actually go somewhere to wait to be picked up, but you'd want it to come to your house. So you want stations equal to the number of actual buildings.
Yeah, so that's a very good point. Actually, the stations, it can be seen as 2 ways. One way is you actually have these stations, our vehicles are actually parked there, but the other way is that you could have just regions where the vehicles service the demands, and customers don't actually have to physically go to the station, so they can just, on their smartphone, dial up the vehicle, and the vehicle will just travel to pick them up, essentially. So in that sense, the stations are more metaphorical rather than real.
We have some time for additional questions. Can I ask the first speaker? So you mentioned that you guarantee that with finite samples, you're going to have these properties. Can you discuss a little bit the convergence rate? Like, how do you get there?
You mean the finite samples?
Yeah, like, can you describe perhaps the rate with which you're improving the quality?
So the current algorithm says if your current policy is not already near optimal, then you will always have a non-zero probability to explore unknown regions. That's guarantees that you always explore unknown regions. But if the policy is already near optimal, you don't have to really explore. That's the case here.
Mm-hmm. Can I ask the second speaker? So what is different with this platform relative to other platforms for the SLAM algorithm that you're implementing?
Okay. So basically, I mean, the SLAM is able to use 4 cameras at the same time. And the difference is that its image point is kind of circle line. And that's how we are able to use the 4 cameras in the SLAM.
Okay, so it's the number of cameras.
Yeah, right.